Assalamu alaikum. This is Sayyid Shahir, a recent graduate from the Department of Computer Engineering, COMSATS University, Islamabad, Attock campus. In this video, I'm going to share an overview of our final year project, which is titled as Non-Contact Grain Moisture Detection and Classification using OFDM-based SDR technology and artificial intelligence. This is the problem statement of our final year project, which states moisture content in grains is a crucial parameter in agriculture, directly impacting storage stability, crop yield, and overall economic value. Traditional moisture detection techniques fall into two main categories: direct and indirect methods. Direct methods, while accurate, are often slow, labor-intensive, costly, and require skilled operators, making them impractical for real-time applications. Indirect methods, such as contact-based sensors, introduce the risk of contamination or physical damage to the samples and typically lack the flexibility needed for rapid, large-scale assessments. Non-contact indirect techniques, though addressing some of these issues, are often expensive and less adaptable to different grain types or varying environmental conditions.
Our proposed solution utilizes the concept of orthogonal frequency division multiplexing, called OFDM, implemented with the help of software defined radio USRP kits, which help us to send RF signals and record them at the receiving end. With the help of those signals and subcarrier data, or OFDM, we can train our AI algorithms, which can help us to detect different moisture levels and also classify them.
The objectives of our final year project are as follows. Our project general methodology can be divided into four major steps. The first step is sample preparation. The second step is the wireless sensing system design. The third step is signal processing, feature engineering, and data analysis. And the fourth step is machine and deep learning model training and classification.
This is our experimental setup. This side is the transmitter side and this side is the receiver side. Our system design hardware component consists of three major components. The one is PC and the other is antenna and NI USRP 2922 kit. This is log periodic printed circuit board antenna, and it is a type of direction antenna, and it is which is the frequency range is 850 megahertz to 6.5 gigahertz, which is connected to USRP kit via SMA connector. The frequency range of this USRP kit is 400 megahertz to 4.4 gigahertz. These LEDs shows the different status of USRP. This is the Ethernet cable which is connected to PC, and this is the input supply power. This is the software part of our system design, which is implemented in LabVIEW. This is the software control panel. From here we can adjust our parameters: IQ rate, carrier frequency, and external gain. This is the LabVIEW code for software defined portion, and this is a wireless channel state information raw data, and these are the same parameters which is in transmitter PC. This is the software defined part.
Now let's have a look at how our project hardware and software combined works and how we collect our data.
Now this is the transmitter side of our project. Here we will run our code of transmitter OFDM frame. Now this is the channel path, the wireless channel, transmitter antenna, receiver antenna, transmitter USRP kit, and receiver USRP kit. Now the receiver parameters are defined over here. The carrier frequency and IQ rate should be same of both transmitter and receiver. The time frame for our one data collection sample is 10 seconds. Here let's run our code. This is the raw data that we have recorded. These activities are repeated for different classes and for several number of time. As my group member gave you a demo, this is the core idea behind our system design, where this part can be seen define the architecture of our transmitter side, and this part is of the receiver side. And the core idea behind how we are gonna detect the different level of moisture is the higher moisture content increases the grain's dielectric constant. It affects the permittivity of the medium, so it results in greater RF signal attenuation. Now this is what the actual time series representation of the whole 10-second activity dataset looks like, and it is completely raw data. Now this is the visualization for only data subcarriers, but as it can be seen that the data is too noisy. Now these are the results after applying Gaussian smoothing. Now the signals have too less noise, and also the edges and amplitude is preserved. This is an overview of our project data analysis and classification part. So our experiment consists of one is done at 1 feet distance between sample, receiver and transmitter and sample, and the other experiment is for 2 feet distance. Both experiments are performed at different frequency, 4 GHz and 3.5 GHz respectively. The dataset is collected at the rate of 250 samples per second, and the activity time for each file or a data file is of 10 seconds. For the data analysis portion, we have performed analysis of variance F-score, signal envelope to construct a single representation of our dataset, and finding means of the maximum value, minimum value and mean of our signals. The classification part is divided into two portions: traditional machine learning and deep learning approach. In machine learning, we have used 5 classification algorithms. These were determined with the help of MATLAB apps that these algorithms perform better as compared to other classification algorithms. In deep learning portion, we have used simple neural networks, multilayer perceptron, and our custom 2D CNN approach. The evaluation matrices to determine which algorithm perform better are the accuracy, precision, recall, F1 score, and confusion matrix. So this is the input window to two-dimensional CNN. Assume this as an image where each pixel value is not a gray level but a magnitude response. Now